Hello everyone, I'm Frank and welcome to Frank Puzzles, and this is today's challenging level puzzle, and it's called Salix by Jay Dyer. And here are the rules. We have normal Sudoku rules apply, which means in every cell in the grid, place a single digit such that every row, column, and designated 9-cell region contains the digits 1 through 9 exactly once each. We need to shade the entire grid with two colors so that each color forms a single connected area and no 2x2 area is entirely one color. So this is called yin-yang shading because it looks like a yin-yang shape it generally has a yin-yang type of shape, or the idea of it, I guess, is yin-yang. And this is an example of a valid yin-yang shading, where the shaded section is all orthogonally connected, and the unshaded section is all orthogonally connected. And what does it mean to be? He doesn't say orthogonally connected in the rules, but that's essentially what a single connected area means. So to go, an orthogonally connected region is basically means you can go from any cell in that region to any other cell in that region just by going through edges, all while staying within the region. So for example, to get from here to here, you can just go along these edges and stay within the region to get to that cell. Same with the unshaded regions. You can go from any cell in the unshaded regions to any other cell in the unshaded regions just by going through edges, all while staying within the region. Now, what's an example of one that doesn't work is, for example, like this, because if you try to go now from the unshaded cells in the region to any other ones, they can get to each other here, but they cannot get to these sections here, except if they go through a corner or if they go outside of the region, which is not allowed. And another example of an invalid shading would be something like this, because here we have a 2x2 area that is all shaded. Another invalid shading would be something like this, because here we have a 2x2 area that is all unshaded, and no 2x2 area is entirely one color in yin-yang shading. And those are examples of how yin-yang shading work and don't work. We have a digit in a cell with an arrow equals the sum of the first n digits of the other color in the arrow's direction, where n is the first digit of the other color in that direction. So this is x sums, but 4 different shadings. And the arrow must point to at least n cells of the other color. Interesting. So a digit in a cell with an arrow equals the sum of the first n digits of the other color in the arrow's direction, where n is the first digit of the other color in that direction. Two arrows in the same cell are treated as independent clues. So that would be applying to that cell there. So so obviously the shading is not going to work because this doesn't have any cells in that direction of the opposite color. And it must, because otherwise it equals 0, right? Okay, so say we had some coloring like this. This would be green or whatever. And say this was 3. Then this digit must be the sum of the first n digits, which is the 3, because that's the first digit. 3 is the first digit seen that is of the other color in this direction. So that would mean this is the sum of the first 3 digits here, which could be something like 314, and then therefore this would have to be 8. Say this was well, we right now have this as green. But say this was like blue, and then blue, and then blue. And these were green. Obviously doesn't quite work for yin-yang shading, but this uses this as an example. And this is green, green, and green. Then this digit is the sum of the first x digits here and the first x digits here, or n digits, I should say. It's x sum, so. But these are treated as independent clues because it's not. It'd be kind of weird to actually not do that. So say then this was basically, oops. Say this was 2 here, and this was 3. And then we had 2 and 6, and this is 3, 1, 4. Then this would also be 8 in that instance, all right? Because the first 2 digits in this direction add up to 8, 2, and 6. The first 3 digits in this direction add up to 8, 3, 1, and 4. And that's an example of how these arrows work. And again, the arrow must point to at least n cells of the other color. So you can't say like have green here, and then this is saying 8, or not 8, 5, because there aren't 5 blues in this direction, because yeah, and this is normal because we don't normally allow counting of non cells that aren't there, right? For exomes. Anyways, those are all the rules. If you like to play along, there's going to be a link in the description. And now, I'm going to get started. Let's go. Okay. So, the most that these cells can point to has to be, this is up to 5. Well, that's not helpful. Up to 5 on these cells. This points up to 4, and this points up to 4. This points up to 6, and that's fine. But that's not really helpful. We need to figure out, essentially, how many you have. Anyways, this has to be one color, and this must be another color somewhere along this row, right? Because otherwise, as I said in the rule explanation, then you're going to have an answer of 0 in the arrow cell, because the sum of the digits of the first x digits is going to be 0 because you don't have any of the other color there. So we're going to color this green and this blue. It's not necessarily, actually, we don't know that's blue necessarily. We know there is a blue, but it could swap again in colors. This is an interesting pattern they have here. So they have that pattern here, they have that pattern here, and same with that. The thing is, for this, it's going to have to be some combination of 2 and 3, I think. It obviously can never be 1 if you're in the same row or column, because and that would basically mean that one of the next color is the sum that you're adding up to, which would be 1. But you already have a 1 in that column or row, so obviously that's not going to work. I guess it could be 2 twice. That is also possible. So we don't have a guaranteed 2 or 3. Um, so for the x sums, it's gotta have to be, unless it's on a diagonal, in a row or column, it has to be 2 or 3 is the first digit seen. Okay. Oh. When they're pointing in each direction. When they're pointing one in one direction, one in the other direction. Oh, you could have a 2 in the middle. So that is possible. But you can't have a 2 in the middle here or here. Because 2 can never be the sum of any x sum, even on a diagonal, right? Because how do you add up to 2? You would have to have a 2. But then by being 2 as the first digit, you have to count the first 2 digits, right? Obviously, 1 doesn't work because 1 just adds up to 1. And again, if you have a 2, so this can never be 2 here. Which means this has to be a combination of 2 and 3 on opposite sides. And this must be a combination of 2 and 3 on the opposite side. So these are opposite colors, necessarily. Because one has to be pointing to 2 in one direction, the other one has to be pointing to 3 in another direction, because they can't point to 1, and they can't point to 4 as the first digit. Because 4, if they point to 1 as the first digit, that means count one digit, which is going to be the 1. If you count 4, you have to count the first 4 digits, which is at minimum 1, 2, 3, 4, which adds up to 10, which is never going to be a digit. And because 2 can't be here in the middle, that means one has to be pointing 2 in one direction, the other has to be pointing 3 in the other direction. And they have to be opposite colors. We could have a 2 here, and then these are the same colors. So that is possible. But in this instance, we have 2 and 3. We have 2 and 3. Which is interesting. So then, because these are different digits, or different colors, they necessarily must see the other. One of them sees its own color here, and then it sees the different color in that cell. And because of that, this has to be a 2-3 pair. Interesting. So then the other one must be 2 or 3, right? Because it has to be the opposite color, and it cannot. Ooh, that's gonna be weird. Then they both have to be 3? Oh, wait, no. So these are going to have to be the same colors here. Right, that's the only way it works. If these were different colors, one of them has to be pointing at... So if they're different colors, one of them is going to be seeing a different color here. And that has to be 2 or 3. Then the other one has to be seeing a different color that way, right? So say we see that, and then this is a different color. So say these are different colors. If these are different colors, one of them sees a different color here. So let's say that's green, so this sees a different color here. That must be 2 or 3. But then this sees a different color here. So that must be 2 or 3. But the problem is, this says, oh, read the first 2 digits. So this is the sum of the first 2 digits, is that. But then this says, that's the sum of these first digits. and they have to be the sum of each other if they are the same color. Or sorry, different colors. So therefore they have to be the same colors because they can't be equaling each other. They can't be summing the other one, which would have to occur if that were the case. So these all must be the same color. We don't know which color though. So we'll mark this as pink, we'll mark this as yellow, we'll mark this as medium. And these have to be the same color then. Which means 2 and 3 have to be after this. 2 can't be here anywhere. So then this has to have 3 cells of the different color here. So this is definitely 3 here, and then these are both orange. And then we have a 2 somewhere here. 3 cannot be any of these. That's going to be problematic. That means we have to have a 3 here. We need another 3, though. Can we have a scenario where one of these is... Okay. Did I overthink this, then? Okay. Say these are different colors. That's a little problematic, though. Say we had a green here. This has to be 2 or 3. So then this is equal to the sum of the first x digits, which includes that one. Yeah, so they have to be the same colors. I think that's a given. Oops. Oh, I forgot. I don't know if I started. Anyways, yeah, so what does that mean? That means this has to have a 2 or 3 here, which means 3 has to be here, and it's a different color. And we have to have a 2 here of a different color. This can't be 3. This can't be 3. These always have to be the same color. And yeah, that doesn't... Okay, so that's why this doesn't have an arrow. Because 2 can never be in the middle. Can 3 be in the middle is kind of the question, right? If you have both of them pointing at 3, that means the first 3 digits of the opposite colors must be seen. Did I even say let's go? I'm just sort of blanking about what I did for the intro. Anyways, so we have 3. Can you have 3 in the middle is the question, right? Because you could actually have something then that actually works. A 3 in the middle here. If you have 3 in the middle, the outsides would have to be, at minimum, 1, 4, and 2, 5. Or 1, 2, and 4, 5. And either way, you can't have 1, 5, and 2, 4, because then they both would have to be 9 adding up. Right? And you'd have 2 9s in the row, which is not allowed. And if you have 1, 4, and 2, 1, 2, and 4, 5, one adds up to 6, the other adds up to 12, which is not a digit. If you have 1, 4, and 2, 5, you have them adding up to 8 and 10, which is not a digit. So no, to have in between, you have to have a 2. which means this is the opposite color. And this must be a 2 here. Because there's no... If we don't have this set up, the problem is we don't have 3 digits to see in this direction and this direction. Right? Because this sees 3 cells this way. So this has to be 8 or 9 here. Because it's a sum of 3 digits, which includes 1 4 or 1 5. With 1 guaranteed here. This sees 2 in both directions. So it's pretty broad here. And this must see 3 here. So this is 3 here. Oh, and I guess we should make that red maybe. So this sees 3 here. That means there must be a 2 in this direction somewhere. It cannot be here. So it has to be here. This is red and is 2. And we don't know how this pattern works. So this is the sum of the first 3 digits, which is without 2. So it would have to also be 8 or 9. We have to have a 2 somewhere here. So there has to be a 2 here. And it's with, at minimum, 4 or 5. So this is also 3 1 4 or 3 1 5. So 2 is here, 2 is here, which means 2 can't be here. So 2 has to, in column 9 has to be one of those 2. So we know this is a boundary. That's not good. Let's do this. We know this is a boundary, this is a boundary, and this is a boundary. We know these 2 are boundaries. So because of these arrows, you can't have a 2 there. You can't have 1. Remaining digits of this row are 4 through 9, right? This can't be 4 because it's 2 plus another digit. It has to be at least 2 plus 4. So this is 6, 7, 8, 9, same here. However, these could be 3 through 9, right? Because it's the first digit, the second digit seen this direction of the opposite color. So red goes here. If this is red this way, then this must be the yellows this way. If it's yellow this way, therefore it must be red somewhere along this. It would have to be one of these. So if this is red because of the 2x2 box that has 3 reds, this would have to be yellow. Which would make that a 2, because it has to see 2 cells. And this would be yellow, yellow. So if this is red, this would have to be yellow, yellow. And then this would have to be all red. If this is yellow, then this would have to swap to red here. Because it can't be yellow all the way. It would have to be yellow here, and then this is red. But then this has to have 2 reds here. So first, if this is red, this must be yellow. Then we swap to red. If this is yellow, obviously, then we swap to red. So either way, this must swap to red here. So if this is red, we have yellow, yellow, yellow here. If this is yellow, these are all yellow too, right? Because the yellow has to orthogonally connect. So if this is red, we have yellow here, which means this must orthogonally connect to the yellows. It must go that way. This can't be 2 by 2 of all yellow, so therefore this is red. Otherwise, if this is yellow, we have all yellows this way, also to orthogonally connect. So this is guaranteed to be all yellows. This is guaranteed to be all reds. Okay, so on yin-yang shading, you can only swap on the edge of the grid colors twice or 0 times. Because, first of all, you can't swap an odd number of colors, right? Because if you swap once, you have to swap back to the other color eventually. And if we try to orthogonally connect, if we try to go red, yellow, how do you orthogonally connect without breaking the other region in two? And the answer is you can't. So if you try to connect the reds orthogonally, that would break apart the yellow into two separate regions when it's supposed to be one region. And if you try to orthogonally connect the yellows, if you have 4 swaps, then you have red broken up into 2 regions. So therefore, once we've swapped once, we've swapped a second time, and we cannot swap again. So orange is the same as red here. So we're going to make reds now blue and yellows green because we want to match that. So therefore, pink has to be green. This is a 2 by 2 with all blues, so this must be green. It must orthogonally connect. This has to be blue all the way around because we've gotten the 2 color swaps already. So then this is green. This is green. We don't know what this is. So this is green. This has 2 here, so this must be these first digits. So these 2 digits add up to that digit. So we have 4, 5, 6, or 7 there. One of these must be blue. We don't know which. So this is blue, which counts the first X cells. It could be 1, though, in this case. This is green. This is green. Okay. This is green. We don't know if this is blue or green. This could be either. We have a 2 definitely here. This is green because of the 2 by 2 area. That's all blue. Same with this. This is green. And if this were blue, it can't be 2 or 3. So therefore, this has to be green, which makes that a blue. To be orthogonally connected. Boundary, boundary, boundary. This is a boundary. This is all blue, so this must be green here. Green has to orthogonally connect. This is 3 greens, therefore this must be blue here. So this is boundary here. This must be 2 or 3. It cannot be 2, so this has to have 3 here. So this is equal to 6 through 9. Because you could still have 2 and 1 there. It could be 1 here and then 2 in one of these spaces. So there has to be 1 blue at least here. It could be 2 blues here. This is done as a region. Or not, this is a boundary. I guess let's do a boundary around the entire grid. Okay. Um, if this is a blue 2, this has to see 3 greens. It could be 1. What we could not have is 3 greens adding up. But this could be a blue 2. And then this... Okay, so... Interesting. If this is blue 2, I guess it could see a green 1 there. That is possible. um... Hmm. Hmm. Obviously 2 doesn't work here. So this has to be either the sum of... Well, it could be actually more, right? Well, no, not really. So this can never be adding this digit with it. Because if you add that digit to the n would have to first of all be 2 or greater. 2 or greater plus 8 is 10, which this can't be a digit. So it can never include this. So either this is 3... So if we had 3, this being the sum of 3 greens, it's because it can't be a 2, because the blue 2, the 2 has to be in the blue region here for this sum to add up. You can either have it pointing to 3 or pointing to 1. You can't have it pointing to 4 because that would necessarily include this cell, which adds up to 4 plus 8, which is 12. So this is 3 or 1 this way. So we're trying out if this is 3. If this is 3, then this becomes green, green, green. That means this is blue and is 2. This has to be green here. For yin yang, so this is going to be problematic because if this is yin yang shading, then you can never have diagonals be opposite colors. So you cannot have this pattern. Because if you want to orthogonally connect the green regions, you will break the blue regions into 2 regions. If you want to orthogonally connect the blue regions, then you have to then you would have to necessarily make break the green regions into 2 regions, which is not allowed. But because of this 2x2 area now, this has to be blue, and we have the deadly pattern in yin-yang shading. Therefore, this cannot be 3. This has to be 1. So this is 1 pointing at another 1. So 1 can't be here. That forces this to be 1 for this to add up to a single digit. That means this can't be 1 here. This can't be 1 here because of the 1 in the row. So this has to be the 1 that is green. So this is 1, which means this is a 2x2 with 3 greens. So this is blue. These have to be blue because these are opposite shading. So this is 2 here. We have 3 blues here. This must be green. Must orthogonally connect. And again, we can't have the deadly pattern here. Therefore, this is blue. We know one of these has to be blue or has to be blue to count 3 digits. And you cannot have a 1 in any of these cells, right? Because 1 because of the box here, 1 here, because 1 in the column. So this must be 3, 2, and 4 adding up to 9. So that's 9. So this has to be 2 and 4 in the blues. And we know one of these is blue. So if this is blue and that's green, this has to be green. If this is blue and that's green, well, we can't have... We could have... So either this is blue and that's green, which would make that green. Or this is blue and that's blue. So, okay, if we have this green, this has to be blue for to count 3 blues here. If it's blue and blue, if it's blue here, this cannot be green because of the deadly pattern, so this must be blue. So either way, this is blue. And this cannot be 3 or 2. To add up to 9, it must be 4. So this is 4, which makes this 5. That's 3, 1, and 5, adding up to 9 here, which eliminates 9 in the rest of the row and 5 in the rest of the row. So this cannot be 2 and 5, adding up to 7, and this can't be 7 here. It must be 2 and 4, adding up to 6, or 2 and 6, adding up to 8, which eliminates 6 in the rest of the row. This is 3, 4, and 2, but we don't know where the 2 is. It could be either of these spots. This has to orthogonally connect, so that's green. This has to see more than one cell because it's not 1. So it must see 2 cells here. So this is 2, and that's blue. I guess I really don't need the borders, though. Yeah. Let's just remove the borders. I usually can spot them now pretty easily. So borders just kind of, I mean, just are sort of extraneous, I guess. At least for me. I used to actually rely on the borders quite a bit, but I can spot them fairly easy now. Green has to orthogonally connect, so this must be green. This is 3, 2, 4, so this sees the first 2 digits. This sees the first 2 digits. It cannot be 2 and 2, so this can't be 4. It has to be, cannot be 2 and 5 because of the 5 in the column, so it has to be 2 and 6 here, which makes this 8. So this can't be 8, this is 6, which makes this 2 and 4 there, therefore that's 7. This must be 2 and 4 in this direction, so the first blue cell must be 4 in that direction. This can't be 8 anymore, this can't be 9. So to add up to this, it can be 2 and 4, adding up to 6, cannot be 2, 5, or 2, 6. So then this has to be 2, 4, adding up to 6 here. This then can't be 4, it's 3, 1, 5 as a triplet, which eliminates 3, 1, 5 in the rest of the row. This can't be 4, 5. This must be 9 to add up to 3, 1, and 5. So no 9 here. This can't be 6 because of 6 in the row. So this is 7. That leaves this as 8 there. No 6 or 9 here. No 6 or 9 here. Where are 6 and 9 in column 5? They can't be here because of 6 and 9 in the boxes. So this has to be a 6-9 pair here. Which means the remaining digits in column 5 are 1, 4, and 5. This can't be 1 here, so this is a 4, 5 pair, which leaves this as 1. And this cannot be the sum of the blue digits then, because that would just be 1. So this must be blue here, and this is green. This is not green. So this has to be green as 2 digits. Cannot be 3, 4, or 5 here. It has to be 6 or 7 here, which forces 8 or 9 there. Interesting. That points to 1. This is 7. So we have to have at least 3 blue digits. But we really can't have 3. And this can't be the first blue digit it sees. So we have to have a blue here. Cannot be 1. This is 2. It cannot be 3. 3 would require 1 and 3 to... Well, I guess it could be. 3 would force this to be blue. But the problem is that's at least 4. Because it cannot be 1, 2, or 3 because of 1 in the row and 2 and 3 in the column. So 3 and 4 already add up to 7, so this can't be 3. This must be 2 here. And we have to have a 5 in one of these two spots. So 5 is one of those two digits. Okay, this is a diagonal of all blue, so this must be blue here, because we don't want the deadly diagonal. Green has to orthogonally connect then. This can never be 2 and 1, so this can't be 3 here. 1 could be here, though, so this could be adding up to 3 still. Okay. Where is 9 in box 7? Can't be here because of 9 in the row, so this must be 9 here, which means this is a sum of 2 and 7, which makes this a 6-8 pair. This can't be 8 because of 8 in the column, so this is 6, this is 8. Okay. Remaining digits of box 8, we have 4, 5, and 7. Okay, and 7 cannot be either of these, so this is a 4, 5 pair, which eliminates 4 and 5 in the rest of the box and row. So this can't be 4, 5, it's 7. This can't be 4, 5. That leaves this as 3, 6, and 8. No 3 here because of 3 in the column. This leaves a 1, 5 pair here. So we have a 1, 5 pair in column 9, which eliminates 1, 5 in the rest of the column, so this cannot be 5. So to add up to 7 here, this must be blue here, and this is 5. So we have 3 blues here. This can't be blue. This must be green. Green has to orthogonally connect. Therefore, the medium gray has to be green, which means the dark is blue. Green has to orthogonally connect, so this is green. This is a diagonal of green, so this cannot be a diagonal of blue, so this must be green here. And it had to orthogonally connect anyways, so that was there. One of these has to be green, the other one has to be blue. So we have to have 2 and 4 adding up to 6, though this cannot be 4. So 4 is one of these two. And that, because one of these is 4, this can't be 4, that's 5, which makes that 4. 4 can't be here because of the 4, 5 pair in the box. So therefore this must be green, which makes this a 4 here. And 2 and 4. Therefore this is a 2 by 2 that is all green, so this must be blue. And the rest, I think, is just normal Sudoku. I think we've... Oh, no, we've got these arrows. Okay. So normal Sudoku with these arrows. So then this is the sum of these digits. This is the sum of these digits, I should say. So this is either 1, 2, 1 adding up to 3, 2, 3 adding up to 5, 2, 5 adding up to 7, or 2, 6 adding up to 8. It cannot be 1 and 5 because of the 1, 5 pair in the column. So this cannot be 3 and 7. That seems fine. Remaining digits of column 1. We have 2, 3, and 7. Okay. And 2 can't be here, 2 can't be here, whereas 2 in column 1, it must be here. So the 2 eliminates 2 here, which means 2 has to be there in column 9. We should have all the 2s now. We do. So, okay, 9 is the sum of 2 and 7. 6 is the sum of 2 and 4 and 2 and 4. 8 is the sum of 2 and 6. 9 is the sum of 3, 1, 5. 9 is the sum of 3, 2, 4. 9 is the sum of 3, 1, 5. 7 is the sum of 2 and 5. 6 is the sum of 2 and 4. 1 is the sum of 1. So we just have these arrows left. We don't know if there's a blue here. This 7 eliminates 7 from being here. Remaining digits of 5 here eliminates 5 here. So this is 8 then. Which means this is a sum of 2 and 6. So this cannot be 8 here. 6 eliminates 6 here. Remaining digits of box 5 are 3 and 8. This can't be 8 because of 8 in the column, so that's 3. This is 8, which leaves the remaining digit in column 4 as a 7. Remaining digits, 4 eliminates 4 here, so that's 5. Remaining digits of column 6 are 1 and 3. This can't be 1 because of 1 in the row, so this is 3. That's 1. So this must be 2 and 3 for the blue. Interesting. 5 eliminates 5 here, so that's 1 and 5, which eliminates 5 here, so it's 1 and 5. Okay. Remaining digits. Let's do column 9. We have 3, 7, 8, 9. This cannot be 3 here or 3 here because of 3 in the box. So it's, and this can't be 8 because of 8 in the row. Okay, remaining digits of row 2. We have 1, 3, 4, 7, 9. This can't be 3 because this must be the sum of 5, 2, and 3 here. This can't be 3 because of the same thing. This can't be 1 here because of the 1 in the box. And this can't be 1 because of 1 in the box. Where is the 1 in row 2? It must be here. So that's 1. This can't be 4 or 7 because of 4, and it can't be 3 because of 3 in the column. So this is 9, which means this can't be 9 here. This has to be green because it can't be the first blues, must be 2 and 3. So this is 2 and 3 here, which makes this 7, which makes this 9. So no 9 here, no 9 here. This is 4, 7 as a pair. Okay. We have 5 digits in row 3, so remaining digits of row 3 are 4, 6, 8, and 9. No 9 here, no 6, 8 here, so this is 4, which makes this 7. This is a 3 green, so this can't be green. This must be blue, and this must be green here because of the 3 blues. We had that already anyways, so... 4 eliminates 4 here. This 7 eliminates 7 here, so this is 4. We have 6, 8, and 9 here. This cannot be 9, so it can't be 6. It's 8, which makes this 6, which makes that 9, which makes that 6. 8 eliminates 8 here, and 8 here. Okay, now we have columns. In column 2, we have 3, 5, and 9 remaining. This can't be 3 or 9, so that's 5. This can't be 3, so that's 9, which makes that 3. Column 3, we have 1, 5, and 8. This can't be 8 here, so this must be 8 here. So this can't be 1 here because of 1 in the row, so that's 5 and 1. 5 eliminates 5 here, so it's 4 and 5. Okay, remaining digits of row 1, 3, 7, and 9. 7 and 9 cannot be here because of 7, 9 in the column, so that's 3, which makes this 7, which makes that 9. 7 eliminates 7 here, so it's 8, which eliminates 8 here, so it's 3, which makes this 6, which makes that 8. That's 3 in the corner because we're almost done. This has to be a 6, and this must be 4 and 7. So this is 7, and that's 4. And that's the solution. Yeah, pretty nice logic throughout. Very, very cool logic. Particularly the break-in. That was a very interesting break-in, right? So I immediately thought of the 2 in the middle, kind of. But then realized that these couldn't be 2. But for some reason, I didn't apply it to this. But yeah. But yeah, you can't have different arrows be pointing at... They would be the sum of each other, which is not allowed, right? Because unless you have a 0 involved, they can't be the sum of each other. So therefore, they had to be the same color. And they all are actually green, which is interesting. Anyways, I hope you enjoyed this solve, and I'll see you next time on Frank Puzzles. Take care.